Thanks for clicking on this video. For those of you who don't know me, my name's Peter, and it's been about 1.5 years since I made a video, so I guess I'm probably pretty rusty at this. Anyway, this is the project that I've been working on here for almost 2 years. I started the design of this back in March of 2021 and did a bunch of CFD modeling on it to come up with the dimensions and how everything works. And basically what we have is a coreless thruster or a coreless ducted fan that's driven by an electric motor, which is integrated in, coils and magnets are integrated in behind the rotor here. And also have the design sort of also has the ability to have the blades with variable pitch in there, so it can be changed while it's running. So it gives you an advantage over a turbofan. And as you'll see, I'm going to take you through this video and show you all the different aspects of this. And you'll see why this is potentially going to be a bit of a game changer in aviation. So let's go and jump right in, and then after that, when I'm all done, you guys can leave some comments on this video and let me know what you think. And if you have any questions, let me know for sure, and I'll try and answer them as best I can. Thanks. Okay, so this is what it looks like in the CAD and with the cowling visible. So let me give you some basic information on this. So the interior diameter here from the inside of the cowling on the bottom to the top is 24 inches, and there's 18 blades in here, and they're each 7 inches long with a chord length of about 1 inch. And as I mentioned before, there was quite a lot of time I spent iterating through this to come up with what seemed like the optimal configuration of this based upon what the CFD was telling me as I was doing simulations on each different variation that I sort of came up with. And as you can see, we've got ventilation in the front here, which I'll talk about a little bit more later on, but let's move on and see how it looks with the cowling off. So this is how it looks with the cowling hidden, and just to give you the basics of how it works. So this blue or purple here, that's the rotor, and the rotor is 1/4 inch thick aluminum, and that's riding on these wheels. So there's a dozen wheels around the front, and there's 9 around the back, and they are basically one of these wheels here, and they have a bearing on either side, or an upper one and a lower one, and that's taking all the driving load from the rotor itself. And then mounted to the rotor, each of the blades has a bracket that it sits on, and they can pivot on that, and I'll show you that in a minute. And on the back side here, we have other wheels here that the rotor runs on, and we also have these other fittings or other brackets in here that allow the blades to be adjusted, and I'll show you that in a minute. Okay, so here's the rotor, and this is everything that's spinning. I've hidden most of the blades here to show you, so I can show you this one actuating. But before I do that, on the outside, you'll see the way I designed this, and this may not be ideal, as I don't know a lot about, or at the time didn't know a lot about the best way to configure an electric motor, but these are all the magnets here, so they alternate north-south facing inwards, and there's 72 on either side, so there's 144 magnets. And the blue thing there, that's the bracket, and the silver one, that's the actual magnet itself. And the coils run in between that. And just to give you an idea here, I'll show you there's one of the coils in there with the bracket that mounts it to the housing. So that doesn't rotate, that just basically sits still in the housing. So, and obviously there's a tight clearance there, and there's a little soft iron core in there, for the electromagnet, and it's just a 3-phase motor set up there with every third one there being on the same phase. So how the blade actuation works for the pitch adjustment, you'll see you've got this orange bracket in here which is running on these bronze bearings, so it can slide, and when it slides forwards like this, it actuates the blade, and you slide it backwards and it comes back. So normally the blade is, as you can see, the blade rotates on a bearing, quite a large flat bearing that's underneath here, and it's sort of in line with the leading edge of the blade. So it rotates around the leading edge. and there's a little roller bearing on the back here to allow this to roll on that flat surface there. So again, if I actuate this, you'll see that's how we get the blades to move. And to actuate them, you're pushing pressure here, but then it's the aerodynamic force on the blade when it's running that's going to pull it back to the flat pitch. So this is just to hold it in place. And when you let go of this, it'll want to flatten out just because of the aerodynamic force on it and where the where the center of pivot is on the leading edge there. So, and I've got 25 degrees of adjustment in there right now. And then this orange thing here, this is actuated by this other ring that's on the main housing, and I'll go back and I'll show you that here shortly. All right, something you may have picked up already is that given that the coils and the magnets are on the outer side of the whole rotor, they have quite a long arm length from the center of rotation. It's about 13 inches of radius. And so the amount of torque available will be really quite high on this setup because of that arm length, and because obviously electric motor has a lot of torque just by its own nature. So that's definitely a plus. And so let me show you how this the blades get actuated here. So you have this other outer ring here, and it's basically slotted, and the slots run on an angle, and then it has wheels on it here that have a flat edge, and they ride up against the flat edge of this orange one here. So while that rotor is spinning, these wheels here are turning and running against the orange one. And in order to get that orange bracket there on the rotor to push forward, this one just rotates. So if I'll move it, and you'll see it as it rotates, it moves forward. And because of the way I've got the animation set up, it's not pushing the orange rotor right now, or that orange bracket right now, but you can see how the wheels there are like overlapping now where it would be. So if I move it back there, you'll see how it comes back again there. So that's how that works in order to get the blades to change pitch. And in order to actuate that, right now for the design, I just have a lead screw in here. And so that pushes along here, controlled by just a regular stepper motor. And that runs this rod here, pushes this rod along, and that rod is sort of hard fixed to the orange, or the light orange yellow one there. And so that allows it to rotate. So that's how you get the pitch adjustment. So the pitch adjustment on the blades would be fully automated and just controlled electronically. And it would work in that if the blades, or if the motor is spinning too quickly with not enough load, then it would just basically course up the blades to add more pitch. And if it's struggling, or if it's laboring under whatever it's trying to do, it would just flatten them out again, very much the same way as a governor works on a regular propeller, so on a constant speed propeller. So that's how that system all sets up. So unlike regular ducted fan motors that exist, because this has variable pitch blades on it, it's not going to have the same problem of running out of steam when it gets to sort of fast incoming air speeds, or fast cruising speeds. The blades can adjust further, and if we needed to, we could actually take this beyond 25 degrees, but I think that'll probably be enough. Yeah, let me tell you some of the other advantages of this design. So having the blades mounted on the outside of the rotor, it gives you the advantage that nothing is under stress, everything is under compression. So when those blades are spinning, they're all wanting to be pushed down into the rotor. It's unlikely that one of them is going to come loose or come free because of that, which is an advantage. And then the advantage of this system, as I mentioned earlier, over a turbofan is that you can adjust the blade angle. So on a turbofan, they're pretty much designed, the blade pitches are set for their maximum cruise, and you don't have that ability to adjust them dynamically. And we don't need to be concerned with blade tip speeds, because the tips are so close to the center there, they're not moving very fast at all. And that's why, as I said earlier, this thing is designed to run at 5,600 RPM. And if you could get bearings that are inside those wheels there that the rotors are running on to handle the faster speeds, you'd be able to run this thing up to like 8,000 RPM. Of course, there'd be a lot more loads and stuff, and the FEA that I did on this for the prototype was all done for 5,600 RPM. So, when I did all the CFD modeling and stuff, I actually did take this up and run some CFD simulations all the way up to a 96-inch diameter, and I'll give you some numbers on that a little bit later. But yeah, as you can see, there's no reason why this wouldn't scale up to a much larger diameter. And with the cowling visible again, I just want to point out a couple of other things. So the stator is in here. As you can see at the back, there's 9 of these stators, and their job is to take the swirling air that's coming off the back of the blades and straighten it back out again, so it comes out the back, in the same angle as the direction of travel. And you can see, obviously, I've set them up as an airfoil, and you'll see later when I show you in the simulation that they actually generate forward thrust because the camber of that airfoil has enough there that when the air's running over the top of it there, and because it's also pitched downward in relative to the direction of motion, there's the component of lift that acts in the forward direction actually provides forward thrust for the whole thruster. So they actually contribute about 15% of the total thrust, just having those in there. And I spent quite a lot of time going through different iterations of the size of those and the cord lengths and the foil and all that sort of stuff to match them up to what the flow was coming off there. And also you can see you've got ventilation in the cowling here, and that's to allow the air to run in past the coils there to keep them cool. And obviously it runs in the front here through these slots and underneath the rotor past the coils and then back out the other side. So that's how that works. And then one of the other advantages of this design, if for some reason you did bend a blade or break a blade or something like that during a trip or whatever, it would be easy enough to come in here, and you'll see I've designed it so these screws here that all have a hex head bolt on them, you just take those 3 screws out there and the blade rotates a little bit and you can just pull it out and you can hot swap it and put a new one in. So you don't have to like do a full disassemble if you've damaged a blade. It's actually like a 5-minute job to do that. There's a couple other things I'd just like to point out before we move on. One of them is one of the big advantages of having this being electric is that unlike a turbofan, it's not pouring a whole bunch of waste heat out the back, which, all that jet fuel goes to burn. There's so much of it that just ends up getting converted into heat and blown out the back, which is such a waste of energy. So this definitely has an advantage over that setup. And last thing I wanted to point out, so anybody who's looking at this who's really astute about aerodynamics would realize that this isn't a good design for where the cowling meets up to whatever surface this is mounted to. I ended up just trying this because it looked kind of cool. But what ended up happening was the airflow here is accelerated right here in front of the blades, the lower blades, and that would create like a pressure differential where it was there's a lot more pressure on the blades here than would be up the top. So I actually added this, and this hasn't been finished yet, but basically a lip similar to what most other turbofans would have on there. This way the air coming in would be even pressure all the way around, and any air that could be accelerated coming off a wing or wherever this was mounted would just go around here below that. And I actually did some CFD modeling on that, and it moves the air pretty smooth and you get a nice even flow in there. It looks kind of different, but as I say, it hasn't been blended in yet. It's just a surface I created there. So anyway, that fixes that potential issue ahead of time. Before I move on and show you how I did the CFD modeling in SimScale, I want to show you the model that I exported out of here, which this was actually before I did all the detailed mechanical design. So it's a much simpler model. It just basically has all the aerodynamic surfaces in it. And I've got it translucent right now so you can see all the parts that make it up. But basically, importing into SimScale, you import like a solid block that has cavities where everything is. So if I make this sort of solid again, and then if I do a cut on here, a section view, you'll be able to see how it's sort of working. So now we're looking into the inside of the cowling there, and obviously the yellow hashed here is solid material. And so if we sort of go through, you can see the profile of the cowling, and then you can see the stators here as they're being cut as you move through, and then you can see each of the blades as I basically move the cutaway all the way around the model. So that's how you import it. And there's also this a section in here which is a rotating section which encompasses where the blades are moving. And I did one of these for this model, and I also did one of these for a two-bladed propeller, for 82-inch blade propeller, just to sort of get a baseline. And I'll make this model available to other people, so if they want to run their own simulations to see what sort of results they can get or what sort of performance that they can get out of it, they're more than welcome to do that. So the first thing I did in SimScale was I wanted to establish like a baseline just to make sure that it was giving me some reasonable results. And so this particular model here that you can see has a two-bladed propeller in there, and I've got it at 82 inches. And unfortunately, all of the simulations that I ran, this was, almost 2 years ago now, magically disappeared out of my account in SimScale only a couple of weeks ago. So I've had to rerun some of the stuff, and I haven't been able to get this propeller one to come up with exactly the same numbers that I did before. But the numbers I got before was 979 pounds of thrust for 195 horsepower, which I was sort of at an 82-inch prop, sort of like a older 182 with a two-bladed prop, somewhere in that category. And I was actually looking this up online to see if people have done some calculations, and this is actually of a 172 here. And someone did this, and they've got numbers in here showing, and this is in kilos, so 220 kilos multiplied by 2.2, you're in the sort of 500 and something pounds of thrust here at 2400 RPM. And when I did this propeller thing, I was doing this at 2800 RPM, so really pushing it. And I remember when I did the Raptor, that had, I think, around about 320 horsepower, and with the 5-bladed prop, I measured it at 1,000 pounds of thrust. So I think 900 pounds of thrust here, 200 horsepower, is probably, reasonable in terms of a baseline. But anyway, that's what the CAD was showing, and you can actually look at these runs here. If I show you this, you can see this black line here is the amount of force, which is the propulsion force. In other words, the air being pushed backwards. That's 3,000 newtons, and down here on this line is the torque. So that's 577 newton meters of torque, and I've put all this into a spreadsheet and done all the calculations, and I can kind of show you a little bit up in here how I've been doing it all, basically just to do my comparison. So this is the one that I had before here, 979 for the two-bladed prop and 195 horsepower. Anyway, so let's move on and look at how I did the thruster here. So here's the thruster model, and as you can see, like I just showed you before in Onshape, and there's the rotating region in there which just encompasses where the blades are. So you import that into SimScale here, and then you go and create your simulation here. So I'm doing a compressible simulation. I select my geometry, which is this one that we're looking at here. And then you specify what your materials are, which is basically air. You can set your initial conditions, and I really don't do much of that. I just set everything to standard. And then you can define your pressure inlet area, and there's different ways of doing this, but I've done it with a pressure inlet on the front, a pressure outlet on the back, and then walls around the side. And that's how I'm defining the working box that everything's working in. And then you've got this rotating region in here which you define, which is it basically looks at the geometry of the blades and it sets those to rotating, and I've got those rotating on a scale here so that we iterate through 1500 time units, and I have it starting out at 0 radians a second, and it works up to 586 radians a second, which is 5600 RPM. So that's how it sort of progressively goes up to that, and then it sort of sits there from time unit number 600 all the way through to 1500, so it can stabilize. And then you can specify details in the simulation, how many time units and how often you write the data, the results and stuff. And then I've got in here the last thing, just specifying the forces and moments on each of the blades there, the stators, and also on the housing. And you run your simulation and then you get your results out here. So if I open up these, I can look at the force plots here. So starting out here, this would be the forces on the rotor. And you see we're negative here just because of the orientation of it. So basically, as it's starting up, it's creating quite a lot of force on the blades themselves. And then once it hits the peak RPM, it sort of stabilizes there and gets to a point where it's just going to be comfortable. So we got 574 newtons there, and the torque on there was 79 newton meters. Sorry. So this is how I'm getting the numbers for how much. Basically, I'm getting the numbers for the torque, but in order to get the numbers for how much flow there is there, I look at the solution fields here. So I'll come back, let this load up, and then I'll come back and show you how it all looks. Okay, so as I mentioned, I haven't been able to come up with exactly the same simulation numbers as before, but I'm pretty close. I just can't remember exactly what specific settings I had last time. When I'd originally done all this a couple of years ago, I actually ended up doing about 167 simulations or 164 simulations on this, iterations where I was just changing one thing at a time, and if it made an improvement, I kept it, and if it didn't, then I reversed it and then went on to the next aspect. So until I got it tweaked in, that's what gave me all the decisions on how many blades and lengths of blades and chord lengths and all the different angles and perspectives and things like the stators and the cowling shape and everything like that. And that's how I basically came to the results that I've got to now. So looking at this now, so this is basically the box that we're in, and I've got the front side of it hidden, or the front wall of it hidden, so you can see in there. I'm going to change it a little bit in a second so you can see more about what's going on. But I wanted to show you how on the back side here, I've got this one face selected here, and over here I can get what the volumetric flow rate is here, so 17.8 cubic meters per second, and I've got that put in my spreadsheet. So this is a new run here, this one I'm working on here, 17.8. So but before, when I did it, I had 18.6, so not far off, but that 18.6 was 114 newton meters of torque, and now I'm only 79 newton meters of torque. So and then of course this is the amount of pressure that's on the blades. And I have a feeling that because of the way this works with the entrainment, with the hole in the middle, that you're getting a free ride with a lot of the air that's going through the middle there. It doesn't have to actually touch the blades, so you're not actually putting force and pressure against the blades, but you are getting flow rate because of it, because it's sort of like acting like a drain with the entrainment effect. Anyway, so the numbers come fairly close here. I had 1575 pounds of thrust before for 90 horsepower. And if you compare that to what I had on the two-bladed prop, 979 pounds with 195 horsepower. If you take those two ratios and just one over the other times one over the other, you end up with this number here. So the performance on the thruster is about 3.5 times what it is for the two-bladed propeller in terms of how much thrust it does for how much horsepower or how much torque is required, given that the RPMs are a lot higher. Anyway, so it's it's a lot. It's a lot better than a two-bladed propeller in terms of efficiency. So anyway, let me rearrange this, and then I'll show you how it looks like with some animations. All right, so I changed the color here of the housing and the box it's in just so we hopefully have a bit of better contrast here. So let me show you this animation here. So what this is basically particles, and I've got them starting out. They start out in this one section of the front of the box here, and then they're just running through and they're showing you the velocity of the flow running through the thruster there. So you can see they're coming in, and that this isn't the way I've got that face set up there is just pressure input, so just atmospheric pressure, and the movement from this is all being actually instigated by the suction effect of the thruster here. So that air would normally be moving at 0 when it starts out. In fact, you can go and change this back to the starting point here, starting point of the simulation at 0, and we should see that update. Yeah, so there's the flow just starting out as it's starting to work up to the first speed. Actually, yeah, that should be, yeah, so that's at 0 when we haven't even got any speed yet. We go to the first time unit there, first 100 time units there, when we're starting to get up to speed, so that's 100 radians a second, and once that loads, you'll see that start to move there, sort of somewhat slowly, but you get the idea. And so that's at 100 radians a second. You can see it. Obviously, the blades don't move in this simulation, but when all the calculations are happening, they're taking that into account that they're moving. That's what that rotating region is for. And you can see how the air hitting the blades is being turned, backwards there, or rotating around in the direction the blades traveling. So we've got a half cutaway now. The blades would be going around in this direction, anti-clockwise, and so the flow coming off of those has now a diagonal direction across that flat surface there, and now the job of the stators is to straighten that out. So they're not doing very much when it's going slow like this, but if I bring the speed up, you'll see how it changes. So we'll go up to basically, once it's all stabilized here at the very end, 1500 time units, and you'll see the extra speed and stuff that's there, or the extra velocity on the airflow. And of course the color changes depending on the speed or the velocity. So the lighter colors means faster velocity. Loading that up, here we go. So now you can see already that the air is moving a lot quicker just because of the color. And so the light green color there is the fastest speed moving through there. And now if I sort of tilt this so you can catch how that stator looks, you can see that the air is hitting the stator at pretty good speed there, and it's actually accelerating across that curved it's lower surface right now, but the curved surface of the stator, so it's faster around there than it is on the other side. So I've got the angles on those pretty good, and possibly have a little bit more angle on there, maybe a little bit more clockwise from what the camera is right now, but you get the idea. So I did lots and lots of iterations like this just to make sure everything was smooth and there wasn't any eddies in there or anything like that. And of course, you can look at this by excuse me, you can look at this just by looking at a cutting plane here and see what it's doing at any given point. So if we just cut it at the midway point here, this will show you the colors based upon the velocities again. So this is going through the blades, and now this is just at the halfway point there. And you can also turn on here these vectors that show you what the flow is like. And of course, the bigger the arrows are, the faster the flow is. And also too, the arrows go in and out of that cutting plane. So the ones that are poking out right now, you can just see them a little bit. It means it's coming backwards towards the camera, and then if you just see the trails of them there, then it means it's going in the other direction. So you can see the stator is having an effect on that one. It's making it turn back inwards again. Anyway, so you can see the flow going on there, and very much the same as what a turbofan is, but the advantages that we have here. And I haven't even done any real work with adjusting the blade angles. I've just got them in the flat pitch. In flat pitch position. I did do some original simulations at 150 knots of oncoming airspeed, like on an airplane that was doing 150 knots indicated, and I did change the blade angles a little bit there just to compensate for it, and I was still getting positive thrust out of there. It wasn't like I'd sort of run out of steam and wasn't getting any net thrust. So the blade pitch is doing what it's supposed to do there, and you know, compensating for the forward motion of the whole setup. So, and you can actually see the entrainment effect going on in here, where, you know, the air in the middle here, this is faster air here than it is out here. So this sort of opening in the middle in here is actually pulling air through, and it slows down through here, but I think a lot of it is just because there's so much acceleration coming off the blades and the stators here. But in the middle here, you know, you are getting a lot more air moving through, whereas, you know, on a turbofan, there'd be a big engine section in the middle here that is just stopping all that. So you're only able to move your air through where all the blades are. And as I said before, I think this area in here in the center isn't having to do too much work with moving the air through there. It's just nothing is really hitting anything. It's just a low pressure out the back here and a high pressure out the front here, and it's just pushing it through or pulling it through. So anyway, that's I think that pretty much covers everything. I'll think if there's anything more to show you about on the simulations here. All right, so I did want to take a couple of minutes here just to give you the backstory on how I was going through these simulations when I was first doing them. So when I started out, the model that I came up with for this was pretty rough, and you know, when I ran the first simulations on it, because of, you know, all the geometry of it, it was actually worse than the two-bladed propeller. I started out, I was at only about 80% the efficiency of the two-bladed propeller, and then of course I started tweaking everything and changing everything, and just you know, one iteration after the other, and I eventually, well, it didn't take me long, and actually I got to 1-to-1 with the propeller. And then I just kept going, and the changes that I made were just making small improvements all the way along. I got to 1.2, 1.3, 1.4, and then, you know, ultimately to 2 times the efficiency of the propeller. And there was never a big change that I made that made a huge difference. It was always sort of iterations. So I was fairly confident that what I was doing was accurate, and I hadn't made any crazy, stupid mistake in the simulation to give me, you know, some wildly inaccurate numbers. But then I started sort of making more changes and doing things, adding the twist in the blades was one of the last things I did, the stators and all the modifications around getting those right. And everything just made more and more an improvement. Of course, when I got to 3 times what the propeller was, I was starting to say, well, this is really a big deal. Now this could make a major difference, because I mean, if you're 3 times the efficiency of a propeller-based engine, what are you compared to the efficiency of a turbofan engine, which is burning tons of fuel and throwing lots of waste heat out the back? Anyway, so when I got to 3.5 times, I pretty much exhausted all the things I wanted to do, and anything else was just going to be a minor tweak. And I was like, well, that's enough for now. And so I was fortunate enough to be able to send off both the propeller model and also this model to a gentleman who is a CFD expert at SolidWorks and was still working there at the time, and asked him just simply on the propeller model, just run it at 2800 RPM and tell me what the thrust number is and tell me what the torque required is. And then I said to him, here's the thruster model. I want you to do the same thing, except this one's at 5600 RPM. And I didn't tell him any dimensions, how to set it up or anything like that. I just sent him the model of the actual thing. I didn't send him the box or anything. And he used SolidWorks, so a completely different tool than what this is. And he set up his simulation the way he would normally do it, you know, for you know, using SolidWorks Flow. And he came up with about the same numbers for the propeller as what I had. And on the thruster, he came up pretty much the same as well. He was slightly higher than the numbers I had on this. So to have somebody completely independent, third party, no, you know, wasn't trying to sort of push him in any direction on how to do it. He just did it his own way to come up with numbers that were similar. I was like, well, you know, there's definitely something here. And that's when I started to do all the work after that to, you know, design the actual physical model and then, you know, think about, you know, getting it constructed. So, yeah, so there's a lot of iterations and stuff went into that, but I was fairly confident that it was going to do what I wanted to do. So, all right, let's move on and see what else I can tell you about this. I know it's kind of long-winded and that, but I didn't want to make 2 videos out of this. I just wanted to do one. All right, you're probably wondering by now, so how are we going to power this in aircraft? And, obviously there's a lot of different solutions that you could do for just a regular sort of piston engine hooked up to a generator to generate electricity. I don't think batteries are a great solution in aircraft, at least not yet. But for a long-range aircraft, any sort of motor generating power with a generator is probably a good solution. Along with a small battery, just sort of act as a buffer, or maybe sort of a capacitor, an ultra capacitor, or something like that. But I've been looking, and I've actually tried designing a couple of Stirling-based generators. They ended up being too large, too heavy, or whatever. And so I've still been scouring the web and looking for other different solutions out there, and maybe this is the one that is probably going to be the best thing here. And obviously I don't have no affiliation with this company whatsoever at this point. They're out of Portugal, and it's called InEngine is the name of the company, and they've got two different variations on this engine, and it's actually a pretty interesting design the way they have it. There's basically 8 opposed pistons here, so it's 4 cylinders, 8 pistons, and works sort of in this radial manner where it doesn't have any real connecting rods or anything like that. And it's lightweight. You can see this is their aero design. This one is actually designed for an aircraft, but like a very small aircraft, almost like an ultralight. And it's like 38 kilograms, and they have the same variant of this. It's 500 cc's. It puts out 120 horsepower. It has the same brake-specific fuel consumption as like a diesel, so 0.32. It is a gasoline engine right now, but I'm wondering potentially this could be a variant of this could be modified to burn jet fuel as a diesel compression engine. And they have a mock-up on the back here for a generator on there. So they're designing it for cars and all that sort of stuff. And you guys can do your own research on these people. You can see the simplicity of their engine. That's the parts for their engine, and that's the parts for a V8 engine over here. So big difference. And they have lots of information on their website here. But if I go and look real quick at their, I think it's their technology. I think that's the one I want. Or maybe that's what I was looking at. Yeah, that's the same one. Oh, maybe not. No, here it is. So there's the 2 engines there. Actually, I made a mistake. That's the Aviation engine there. That's purely air-cooled, and that would be ideal. If you could have something like that was air-cooled, but have it burn diesel, that would be great. So yeah, it's like a slightly different design there. So the spark plugs are in the front there, and this one, the spark plugs are on the sides. So anyway, you guys can do some research on there and read all about this. This little video here shows it running and shows it how it works, and you'll see there. Basically, I'll just pause that there. You can kind of see how the pistons are all running back and forth there. So there's not a lot of moving parts, and it's super smooth. And I'm sure with a good muffler on there, you could make it super quiet. And it is lightweight. It puts out enough power. You could have 2 of these in an aircraft, for redundancy, and each one would have plenty enough power to power one of these thrusters. So anyway, that's kind of what I'm looking at right now as a possibility for power generation for this, but I'm open to different other ideas. Anyway, if you wanted to look up this company and find out more about it, it's inengine.com. So yeah, that's about what I've got for you on the whole idea of generating electricity for this. All right, let me give you a few pictures of me putting this together, or at least the aftermath of it. So these coils that I designed and wound here end up having like a really high back EMF. So it's taken a lot of voltage to run this. So probably in need of a bit of a redesign from someone who's a bit more of an expert of designing an electric motor. The blades came out really nicely. The shop that I had that made the housing and the rotor did a really horrible job on everything. Took 6 months and cost a lot of money, and that rotor was not even round when I got it. It was 2 inches out of diameter in one direction compared to the other, and the edge isn't even true. So it doesn't run very smooth at all, but I mean, it is prototype. Anyway, so I don't really want to be able to try and run it up to more than 1,000 RPM. In order to do that, I'm going to have to get a lot more batteries, and I'm kind of run out of time right now. So I might just leave that up to the next person on their prototype to build and see what they come up with. But anyway, as you can see, there's all the different construction. Those wheels, the black wheels, are Delrin acetal material, and they actually run really smooth on the aluminum there. I don't think that'll be an issue up to high speed. When I'm running it at 100 RPM, nothing gets hot on there. It's all quite smooth and doesn't really have any issues or whatever. Unfortunately, the control that I have right now doesn't allow me to do much with it as well. One of the problems is that it has so many poles in it, so 72 magnets, 144 altogether. It needs a controller that can run at a high frequency. And the one I have can do that, but it just needs a lot more power right now. So I'm kind of stuck with it is what it is for the prototype right now. And obviously I haven't gone to any of the trouble yet of doing anything with the blades and the automatic pitch adjustment in there right now. Those are all bolted in place so they can't rotate. I purposely designed it so I'd be able to do that without having to get all the fancy stuff in there. As you can see, it runs fairly smooth for what it is. This is only at 100 RPM, and of course at 100 RPM, because the thrust is proportional to the speed, the square of the speed, it's not putting out much air right now. You can stand behind it and you can feel the air flowing, but it's not really a lot. But you could imagine at 5,600 RPM, it's a crazy amount of thrust coming out of there. So yeah, so that I think if somebody could design the electric coils better on this thing, I think it would be a good working solution on there. Okay, so what's next for this? Well, I've already filed the patent, and it's apparently going to be public on March 9th. It won't be approved yet, but the patent office says it will be public by then. I'll paste the link in the description of this video once it becomes available. I'll actually show it to you here shortly, some of the paperwork from it. But I think it's time for this to be sort of made open to other people, so other companies who might be building these. I mean, any sort of company that's building electric motors, or probably the turbofan companies or whatever, they might be interested in this, or they might say, oh no, this is no good for our business, it's going to destroy our turbofan business. Anyway, we'll have to wait and see. And then once the patent gets approved, when and if that happens, then I'd be open to licensing for this. But this can scale up to the airlines, and as I said before, I had one of these scaled up to 96 inches, and it was putting out 100,000 pounds of thrust, so equivalent to a big turbofan that's like on a Boeing or Airbus right now. So it could make a huge difference, and of course a lot of these eVTOL companies that are doing their air taxis and stuff, they may want to look at this as a propulsion system as well, given that it can be so much more efficient than open propellers. And it could potentially give the existing aircraft 3 times the range of what they currently have. So, and then with respect to the turbofan industry, that's a $100 billion industry a year, building turbofans for airliners. So that's a big market this is potentially going to disrupt. So let's have a quick look at the patent. All right, so here's the patent. At least this is the filing receipt for the actual filing that was done. And I've had reputable patent attorneys in San Francisco do this for me. So that's basically that. And here is the filing. So I'll go back up to the top here. So there's a lot of pages and a lot of words and a lot of details about all the different aspects of how this works and what all the claims are and everything like that. And I've also filed the PCT for the option for international patents as well with the participating countries that work on that program. And then lastly is all the diagrams and stuff, and all the figures that show the different aspects of it. And this actually came out really nice. So I've got all the details in there about how the various different aspects all work for the design and such and such and such. So anyway, you guys will be able to see that when it's online, at least from what I've been told. Shows all the details there about how the blades rotate and the bearings and all that sort of stuff that I talked about in there, and the actuator and all that stuff. So anyway, you guys can look through all that at your own leisure when it becomes available. So let's move on and let me talk a little bit about a potential application for this thruster that I'm most interested and excited about. All right, well, I'm not going to spend a lot of time on this because I'm going to do a whole separate video on this that I'll link in the description of this video. And a lot of you watching, I've obviously seen this aircraft before, but last time you saw it, it didn't have, it had a thruster on here, but it had a center section in there because I didn't want you guys to see what I was working on yet, because that was the big secret thing that I'd been working on all this time. But anyway, we've got a pretty capable aircraft if we have this set up here, because if two of these with 1,500 pounds of thrust on them each, that's 3,000 pounds of thrust. And this aircraft, are hoping to try and talk an automaker into building it on a production line out of aluminum and building them in quantities, maybe 30,000 a year, trying to get the price between maybe 100 and 120,000. And I think there's a lot of money to be made for the company that does that, because this is actually much simpler to build than what like an SUV would be. But anyway, there's some cool stuff that you guys haven't seen yet. For those ones who have seen this, is that if we do this and we do this, see if I can make it work, and we do this, we now have the option to have a full VTOL aircraft. So we can transition into vertical hover for takeoff and landing, and still, end up basically doing 300 knots true airspeed on probably as little as maybe 11 gallons an hour because of the efficiency of the thrusters. So with the three thrusters here, one on each of three corners, you have 4,500 pounds of lift. And so a 2,500 pound aircraft would have about a 2,000 pound useful load on there. Obviously take away fuel from there, but the fuel burn on this would be a lot lower anyway because of how fast you're going. Most trips, the savings is all in what these thrusters can give us. So yeah, and I think if we can talk an automaker into building these in a lot of numbers, we can turn these into air taxis. At least half of them be air taxis and half of them for private ownership, and really create something that's pretty special. Anyway, I'm going to link this in another video so you can get all the details and stuff about this and watch that in a separate video. So anyway, let's see, what else do I have for you? I don't think there's too much more.
All right, so indulge me for a minute while we do some calculations to compare this thruster to a large turbofan. And the one I've picked is the GE9X. So how I'm doing this, started out with the thruster at 24-inch diameter, and we're scaling it up by 4 times. So 4 times in every direction, X, Y, and Z. And so we end up with a 96-inch diameter, and then the 3-dimensional scale factor, so in other words, the weight and the thrust and the fuel consumption, everything like that, would be the scale factor 4 to the power of 3, so that's 64 times. So if we take the thrust at 24 inches, 1,575 pounds, we end up with, multiplying that by 64, we end up with 100,000 pounds of thrust. And if we compare that to the GE9X, that's 110,000 pounds, so it's sort of, in the similar ballpark. So it's a fairly, decent comparison, and that one there has a diameter of 134 inches, so it's quite a lot larger in diameter. And then the weight from the Onshape model, the projected weight on the thruster is 175 pounds. And so if you scale it up, times 64 is 11,200 pounds, and then the weight on the GE9X is 21,000 pounds. So, it's almost half the weight, or slightly more than half the weight. And then the thrust to weight ratio is 9 for the thruster, and then obviously 9 for the larger one as well. And then the thrust to weight ratio of the GE9X is 5.18. All right, so now the fuel consumption, this gets a little bit more tricky because there's not a lot of information on this, and I actually did find where somebody has picked up this from a 777-200. This is the fuel burn at different altitudes and different cruise power settings. So I've read that the GE90 engine, which is this one is from, is 10% less fuel efficient than the new GE9X. So if we take this 9,700s as like a max cruise, so that's 87%, or actually 91% N1. And then over here we're going to use a cruise one here, which actually could go to lower, but it's pretty much the same all the way across the board here for this different altitudes. You still end up with this much lower number here, and this is pounds per hour. So if we work that number in there, I've said 90% of a GE90, which I've also read is around about 1.2 kilograms per second of fuel. So that works out at 3,960 kilograms an hour, which is 8,712 pounds per hour. And again, this is max power. So that is gallons per hour is 1,300. So that's divided by 6.7. And so the estimate for the small thruster would be 5 gallons an hour for how much horsepower it is, and so the larger one would be 320. And so the performance gain on that would be 4 times the efficiency, which is crazy insane. And then if you go to some cruise numbers here, as I said before, I've taken that, so you end up with 4,244 pounds per hour for the GE9X. Again, just total estimates here. I can't guarantee any sort of accuracy on these, which is 633 gallons per hour. And so the performance improvement there would be 3.3. And if looking at the capacity of the Boeing 777, this is on the 300 version there. It has 171,000 litres, which is 45,000 gallons. It would give it a cruise range of 35 hours, which seems a lot, but maybe that's what it is. I don't know. It's very hard to find information on this. But either way, it's interesting because, I mean, these numbers here is what tells the story. If you had one of these scaled up engines inside of, a 777 and you only need a quarter of the fuel, what does that tell you? I mean, what does that give you? You don't have to carry all that extra weight and the cost and everything. It makes a massive difference. So anyway, again, these are just numbers. If someone else wants to run them, I'm more than happy to see what you come up with. I would be really interested to see someone else's calculations on this.
Let me finish by asking you to leave a comment and let me know what you think of all this in the comments of the video, and share it with your friends and anybody else that you know who's in the aviation industry who might be interested in this. And we'll see how things progress with this. I'm hoping that it's well received and some other companies can pick it up and use their more resources that they have than what I had, and get a few of these built and see what they can really do, see what the performance really is. So thanks again if you're still watching and you made it all the way to the end. I really appreciate your time for watching this. And look out or take a look at the other video that I have linked in this one, and we'll catch you over there. Cheers.